In this video, we're going to talk briefly about nuclear binding energy. Nuclear binding energy is very well named because it is quite literally the energy that is holding a nucleus together, and it could be calculated by measuring the energy change that would happen if you took all of the nucleons required to make a nucleus and brought them together to make the nucleus. So your product would be your nucleus, your reactants would be your protons and neutrons, and as it turns out, there is a mass defect. The mass change is negative. The nucleus weighs less than the total mass of the protons and neutrons that came together to make it. Now, it's actually very difficult to track down masses of nuclei. What we tend to find instead are masses of atoms and isotopes, but that's okay. It's easy enough to get from a nucleus to an atom. All you have to do is add electrons. So on our product side, if what we have available is the isotopic mass instead of the mass of the nucleus, that's fine. All we have to do is make sure we add those electrons in on the reactant side of the equation. And so therefore, to calculate the nuclear binding energy for any nucleus, all we have to do is take the mass of the nucleus and subtract off the mass of the protons and neutrons involved, or usually, because it's easier to find the right data, take the mass of the individual isotope, and that has to come off a special table. It's not coming off the periodic table. Remember, the periodic table is average atomic mass. Here we want isotopic mass. And then subtract off the mass of all the individual subatomic particles that come together to make that isotope. So all the protons, all the neutrons, all the electrons. That's going to give you a negative value for delta M, a mass defect, multiply by the speed of light squared, and you're going to get a negative value for delta E, meaning energy is released when the nucleus is made. Now, if you think about it, really big nuclei are going to have a lot of protons and neutrons coming together, each of them giving off a little bit of mass as the nucleus takes form and holds together. And so if we just used that delta E as our raw value and compared those, it would look like the larger nuclei were more stable than they actually are. So what we tend to report, and what we'll be looking at in the diagram on the next page, is actually the nuclear binding energy per nucleon, EB, here, in which we take that nuclear binding energy and divide it by the mass number, the total number of nucleons. And that way we scale our nuclear binding energy so that we can actually see which of the isotopes are more stable and less stable. General rule of thumb, if the absolute value of the nuclear binding energy, so if we have a large absolute value, because some people like to report these things as positive numbers, even though energy is released, and energy as released is negative. If we have a large absolute value for delta E, and then we wind up with a large absolute value for the binding energy, then we're looking at a relatively stable isotope. So let's see how that plays out in real terms. This is a graph comparing the binding energies per nucleon. So this y-axis here is in binding energy, and the values have all been made positive, so it's actually absolute value of the binding energy per nucleon for a bunch of different isotopes, all sorted by mass number. And you'll notice that there's a really, really big spike here for helium-4. Our graph is generally this nice, smooth curve. La, 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 just like this. Except for that one helium-4. So helium-4 is unusually stable for its size. Why is that? Well, it has what we call a magic number. It has 2 protons and 2 neutrons, and that combines to make an extra stable nucleus. And this is why the helium nucleus is such a common byproduct of nuclear reactions. This is why alpha decay is a thing, not bismuth decay or lithium decay or carbon decay. Why it's always helium decay. Why it's always the alpha particle that we see so often in nuclear reactions, because it's unusually stable. If we ignore helium, then what we see is that the stability generally increases with mass until we hit kind of a happy space here in the 50 to 80 mass number region, 50 to 80 nucleons, and then the binding energy slows down, reduces a bit. So this then allows us to predict which elements might reasonably undergo fusion and which might reasonably undergo fission. The elements that undergo fusion tend to have fewer than 50 nucleons in the nucleus. They tend to have mass numbers lower than 50. And then as they stick together to make bigger isotopes, they head toward that region of greatest stability here. Fission, on the other hand, tends to be observed for large isotopes that are breaking down into smaller pieces, heading toward, again, that region of greatest stability. And so this graph here explains to us why it is that small isotopes tend to undergo fusion, large isotopes tend to undergo fission, isotopes with mass numbers in that 50 to 80 range tend to not undergo either, and alpha particles are very, very common products of nuclear reactions.